Hi, good afternoon. My name is Anita Vogl, and I'm from the Media Interaction Lab at the University of Applied Sciences, Upper Austria. And today I will present StretchEBand, a stitch-based stretch sensor. And this is joint work between the Media Interaction Lab and Google. So we know a broad variety of stretch sensors. So for example, researchers made knitted sensors which can be perfectly embedded, but nevertheless the production process needs to be planned ahead, and designers have to think very carefully about positioning and layout. We also had painted solutions which are easy to make, but depending on the base material, they can influence the comfort of use, and furthermore the durability is an issue. We also know fabric solutions, also commercial solutions which add an additional layer to the textiles, and therefore they are not always the best way to use it. We also know other solutions like flexible solar panels or conductive rubber cords, which are easy to integrate, but their form factor is often very limited. Therefore, we developed StretchEBand, a stitch-based stretch sensor. And this sensor can be implemented into several application scenarios. So for example, for around the device interaction on a smartphone, for enhancing the interaction space of a smartwatch, or enhancing everyday objects. To build stretch sensor or StretchEBand, we evaluated 5 yarns of this broad variety of yarns. So we had conductive yarns and partly conductive yarns. We had yarns based on staple fibers and yarns based on filaments. And so what does that mean for the sensing? If we look at it into much more detail, we can see that staple fiber-based are made of the short pieces of yarns. So they work similar as an FSR sensor, and when the short pieces of yarn touch each other, the resistance changes. Here you can see the short pieces. And we had 2 yarns there. And what you can see here is this decreasing resistance change. Furthermore, we had filament-based yarns, and in contrast to staple fibers, filaments are almost endless pieces of yarn. So a filament-based yarn is made of different filaments, and they are lying next to each other or they are twined together. And if we stretch on these filament-based yarns, each of these filaments becomes longer and thinner, and therefore the resistance changes again. Furthermore, as we are talking about plated yarns, we also have to consider cracks in the coating, which can also influence the resistance. We had 2 yarns based on filaments, so the silver-plated nylon here and the resistive thread here. And what you can see here is that the silver-plated nylon yarn is very straight, and the resistive thread tends to make loops, and those loops are not the best for the sewing machine. Therefore, we chose the first yarn for our further experiments. As we now know which yarn we want to use, we investigate the different stretchable stitches which are typically available on a household sewing machine. So we had the zigzag there, the double overlock, and a super stretch stitch. We took those household sewing machine and put the conductive thread into the bobbin case and the non-conductive one to the top. As previous researchers already suggested, it's always the best way to put the conductive to the bobbin because it then can more easily float and it does not so easily tear. Then we can find our 3 stitches there, so the zigzag, the double overlock, and the super stretch stitch. And what we did is we made a huge amount of samples, so first of all for the different stitches. And we put it into a measurement system where we stretched, stopped, and measured the resistance 37 times for 10 cycles to the maximum stretching amount and back to the minimum. And the total stretching amount here of our base elastic fabric was around 170%. We then got a response behavior, so the resistance change over time. And what you can see is that the zigzag pattern has an almost continuous change to the peak and then back down. In contrast, the super stretch stitch as well as the double overlock stitch seem to have a lot of inconsistencies. So what's the reason for that? If we look at the double overlock stitch, we can see that it uses a high amount of yarn. So where does this yarn exactly float? And how does it influence the sensing? So if we look at the backside where the partly conductive yarn is floating, we can see that the yarn is overlapping here. So as this is not isolated and it's partly conductive, there are some conductive strands inside. And those strands can touch each other and then lead to short circuits. And as the sample is not always stretched completely the same way, this leads to those inconsistencies in the response behavior. Next, we had the super stretch stitch, and the super stretch seems to be very similar to the zigzag pattern, but every second line is perfectly horizontal. So if we look at the back side, everything seems fine, so no reason for the inconsistencies in the behavior. But if we look at the front side, we can see that the yarn is again intersecting, so there are some intersecting loops and there are again short circuits. So it would not be possible to use it for the StretchEBand. Therefore, we then evaluated the zigzag stitch, and the zigzag stitch is equally distributed along the seam, and it looks very simple. And there are no intersections and no overlapping, so it works. As we now know which yarn we want to use and which kind of stitch we can use, we were interested into the stitching properties. So the overall question here was, how can we adapt the stitch to fit the elasticity or the stretching amount we want to use and to reach an optimal sensing behavior? And therefore we split it up into two parts. So the first question is, how wide should the stitch be for a fixed length and a fixed stretching amount? And one sample would be some kind of net structure, because if you have some kind of net structured fabric, you're limited in the stitch length, so you can only stitch there where there's a fabric. So you have a fixed stitch length. And also the stretching amount is given by the material, so we were interested in the stitch width. And therefore, we created a formula where we put in the stretching amount which our basic material has, and the stitch length we want to use, so the distance between the holes, for example, in this case. And what we get is the optimal stitch width to reach the best sensing behavior there. The next question was the counterpart. So we have a fixed width and a fixed stretching amount and want to know how long should the stitch be for that. And one sample would be if you imagine something like a pocket sensor, so at a pocket opening, you may be limited in the space where you can put in the zigzag pattern, so you have a fixed stitch width. And also the stretching amount is again given by the material, so you were interested in the length. And this is done with the second part of the formula. So we can put in the stretching amount and the stitch width and get out the stitch length for our sensing. Okay, now that we know how to make such stretch sensors, we were interested in how users perceive such kind of sensors. So we had two different sensor lengths, two elasticities, and three stretching granularities. We had 12 participants, 8 female and 4 male. The mid-age was around 30, and only one was left-handed. The study setup looked like this. So we had a wooden plate, and the wooden plate was fixed on the table, and a StretchEBand was fixed on the wooden plate so that it was holding there. And participants were introduced and started by calibrating the sensors. So they stretched a few times, and we fixed the minimum and the maximum, because stretching is like handshaking, so one shakes very strong and one very light. And then they saw a percentage on the screen. So this was the stretching amount to which they should stretch the StretchEBand sensor. So 100% was full stretching, and in this case, 50% was half of this. So participant stretched, and where they thought to reach the point, they pressed the foot pedal. And then we looked if this point was within a range. So here for 50%, between 25 and 75%. The overall question here was how the sensor length and elasticity influence the control of the sensor. And what we found is that designers are very flexible in the form factor, so the sensor length has no influence there on the performance. But if we look at the elasticity, we can see that less elastic materials, so for example, stiffer materials are easier to control, and this could be very interesting for ice-free interaction or interaction in mobile context where you need quick access and fast control of your devices. The next question was, how can users control different stretching levels? And here we found, although we calibrated the sensor for each participant, stretching sensation is very diverse. So fixed thresholds would not work, as not only the stretching amount of one level, also the distances between the stretching levels is very diverse between the participants. So we would suggest user-dependent boundaries there. And now that we know how users perceive our StretchEBand, we were interested into the interaction techniques, and therefore we came up with 5 different interaction techniques. So a one-directional stretching for attached sensors, one-directional stretching for like wristbands, so for loops, a fold and stretch technique where we use 2 sensors aside, so either if you stretch left or right, you can estimate the direction. A lift and press technique, so a combination of the stretch sensor with a pressure sensor, for example, pocket openings or pockets on a bag. And a touch and stretch technique as a hybrid interaction technique. We took those interaction techniques and made some applications there to show the wide variety where you can use the StretchEBand. So we made a smartphone application where we used it as attached sensors, so when you're wearing gloves. We used it for enriching the interaction space of a smartwatch, as many other researchers already did. And we integrated it into everyday objects, so for example, for a car seat control. And we put it into everyday objects like a pillow or a toy, and so on. So the contributions of our work is the investigations of urines for stretch sensing from both a textile and a technical perspective, the very quick fabrication method with a household sewing machine, and the scale-able approach, because you can scale up the stitching pattern. As future work, we see potential in making the yarn itself elastic, because then you're more flexible in the stitch. Then to combine stretch and, for example, pressure sensing into one fabric. We are also interested in the durability and in the robustness of the sensor, because there could be a much more intensive evaluation. And we feel that there is a high potential in combining conductive materials with textile processing methods to create a wide variety of sensors. So I'm at the end of my talk. I want to thank you, all the great people there, so Patrick, Theo, Joanne, Alex, Michael, and all the other great people in the lab, and I'm open for questions now.
I'm Madhur from CU Boulder, and I was wondering if you noticed any change in characteristic after several uses, any kind of hysteresis or like loss of signal after a lot of use.
Yes, you're right, because when you stretch it multiple times, so very often, the stitch get a little bit loosened, so there's a drift in the signal then at the end.
Is that something you're looking to improve in later iterations? Or?
Yeah, I think it could be made with a more elastic yarn. So if the yarn is itself elastic, this would be a great way.
Thank you.
Hi, I'm Laura Devendorf from Boulder. So since you kind of rolled out the double overlock and the super stretch because of the shorts, I'm wondering if you think if you had like a core spun yarn that had the conductive element in the core, or a yarn that used a enameled conductive element, if those stitches, do you imagine, would they have a better performance?
So do you think if the yarn is itself isolated?
Like if
Yeah,
the conductive element is...
I think maybe it could work, but
Okay.
the zigzag pattern is the most simple pattern, so yeah, maybe it's still the best pattern then.
Yeah. Well, thank you.
Thank you.
No problem. Hi, great work. I am just curious, like what kind of interactions are possible? Are only the different type of stretch you showed, or can you like I saw the Google project where they have this jacket where you can swipe over it and it has different kind of interaction. Is this based on the same thread? And then does it only have stretching or other types of interaction also?
A great question. Currently, it's only about stretching.
Okay. And is this the same as the Google's the project? Is it using the same threads, or is it different material?
The Google project is different because it's a woven textile.
Okay. Thank you.
Hi, Danielle Wild, University of Southern Denmark. It's just a technical kind of comment or question. I'm wondering if you tried doing your zigzag stitch with a 3-step, because in my experience I found it to be a lot more robust in terms of managing the stretch over time, dealing with problems like hysteresis, like other different kinds of machines, sort of, more machines that have been developed for industrial use purposes.
Currently, we didn't try that out because we focus more on a do-it-yourself approach, which is easily available, but it would be a great idea to check this out if it works better.
Thank you.
Great presentation. I wonder how scalable extension it is available currently.
How scalable this approach is?
How scalable extension is it available at this point using that technology?
Currently, it's limited in the sewing of the sewing machine. So, yeah, up to this point.
Okay, thank you. Let's give a big hands to